There are 6,000 people on board. The kitchens are running, the pools are full, and one machine below the waterline is powering all of it. To understand the scale, think about the Icon of the Seas, currently the largest cruise ship ever built. It is 365 meters long. It weighs over 250,000 gross tons. It carries up to 7,600 passengers and 2,350 crew members. It has 20 decks, 40 restaurants and bars, 7 swimming pools, and its own water park. By common sense, something that large and that heavy should barely be able to move, let alone navigate precisely into a narrow port berth after crossing an ocean. But physics and engineering say otherwise. And everything you see on a modern cruise ship is the result of over 2 centuries of naval architecture, failed designs, and relentless refinement. The origins go back further than most people expect. The first ocean-going steam-powered passenger ship crossed the Atlantic in 1838. It took 15 days. The ship was cramped, coal-fueled, and brutally uncomfortable. But it proved something fundamental. A machine could move people across an ocean on a schedule. In 1906, the Mauretania set a transatlantic speed record that stood for over 2 decades. In 1936, the Queen Mary raised the standard again, combining speed with luxury on a scale never seen before. Then in 1972, the first purpose-built cruise ship, the Song of Norway, redefined the concept entirely. It wasn't about getting somewhere, it was about the journey itself. After that, ships grew larger, faster, and more complex with every decade. But despite all the innovation, the core challenge never changed. A cruise ship is always about one thing: moving an enormous amount of weight through water as efficiently, safely, and reliably as possible. So, how does something weighing 250,000 tons actually move? The answer lies in 2 fundamental principles that govern every modern cruise ship ever built. The first is diesel-electric propulsion. Most people assume a cruise ship works like a car. A big engine turns a shaft. The shaft turns a propeller. The propeller pushes water backward, and the ship moves forward. That is how older ships worked. Modern cruise ships do something far more sophisticated. The main engines on a modern cruise ship are not connected to the propellers at all. Instead, they are connected to enormous generators. Those generators produce electricity. That electricity powers electric motors, and those motors drive the propellers. The entire ship runs on electricity that it generates for itself. This system has one critical advantage over a direct mechanical connection. The diesel generators can run at their most efficient speed, regardless of how fast the ship is traveling. Whether the ship is doing 5 knots maneuvering into port or 22 knots crossing the Atlantic, the engines operate at the same optimal speed. Only the amount of electricity sent to the propulsion motors changes. The result is a significant reduction in fuel consumption across the entire voyage. The second is the azipod. This is where modern cruise ship engineering diverges completely from anything that came before it. A traditional ship has propellers fixed at the stern, pointing backward, combined with a separate rudder to steer. An azipod replaces both with a single unit. It is a pod mounted beneath the hull, containing an electric motor that drives a propeller. The entire pod can rotate 360 degrees. To go forward, the pod points backward. To go backward, it points forward. To turn, it rotates to the side. There is no rudder, no complex steering gear, no long propeller shaft running the length of the ship. The ship can move in any direction from a standing start. A cruise ship equipped with azipods can slide sideways into a berth, spin within its own length, and hold a precise position in open water without anchoring. That last capability deserves more attention than it usually gets. Dynamic positioning uses GPS data, wind, sensors, and wave sensors to fire the thrusters automatically and keep the ship exactly where it is without any human input. This is not a convenience feature. It is a critical operational capability. When a cruise ship anchors off a tender port and passengers are ferried ashore by small boats, the ship must hold its position within a few meters for hours at a time in wind and current. Without dynamic positioning, that would require constant manual thruster adjustments by the bridge crew. With it, the ship manages its own position continuously and automatically while the crew focuses on everything else. But propulsion is only part of the story. Here is what most passengers never think about. Approximately 85% of all the power a cruise ship generates goes directly to moving the ship through the water. The remaining 15% powers everything else. Every cabin light, every air conditioning unit, every kitchen, every elevator, every pump, every screen in every corridor. The entire hotel operation of a ship carrying thousands of people runs on 15% of the total power output. That number is worth sitting with for a moment. A ship the size of a city block, with thousands of cabins, dozens of restaurants, multiple entertainment venues, and a full water park, consumes less power running all of those systems combined than it does simply pushing itself through water. That is how dominant the resistance of the ocean is, and how much energy is required to overcome it. The power distribution system that manages this is comparable to a small city grid. Hundreds of miles of cable run through the ship, carrying electricity from the generators to switchboards, and from switchboards to every system on board. High voltage power goes directly to the propulsion motors and the bow thrusters. Lower voltage feeds the passenger areas after passing through transformers. Emergency generators are located in a completely separate part of the ship, isolated from the main engine rooms so that a single catastrophic failure cannot cut power to critical systems simultaneously. This redundancy is not optional. International Maritime Organization regulations require that every passenger ship over 120 meters, built after 2010, must be able to return to port safely after any single flooding or fire casualty. That means 2 separate engine rooms, double cable systems, and each engine room must individually have enough power to move the ship on its own. The regulation is called Safe Return to Port. It exists because a cruise ship in the open ocean cannot call for external help the way a car can pull over and wait for a tow truck. Everything the ship needs to survive must be on board and fully redundant before it leaves port, not as a backup, as a standard requirement. The water systems operate on the same principle of complete self-sufficiency. A cruise ship at sea cannot resupply fresh water at will, so it makes its own. Onboard desalination plants process seawater through reverse osmosis membranes, stripping out salt and impurities to produce drinking water continuously throughout the voyage. A large cruise ship can produce hundreds of thousands of liters of fresh water per day from nothing but the ocean around it. Wastewater is treated on board before discharge. Solid waste is processed, compacted, and stored for disposal in port. The ship is not connected to any external infrastructure. It is a closed system managing its own resources across days and weeks at sea. There is one final detail that most passengers never consider. When a cruise ship is docked, the main generators are taken offline entirely. Propulsion takes up 85% of the power demand. Without propulsion, the remaining hotel load is small enough to be handled by smaller, more efficient auxiliary generators. More and more ports are now equipped with shoreside power connections that allow ships to plug directly into the local electrical grid while berthed, shutting down all onboard generators completely. The ship sits in port running on the same electricity that powers the city around it. No fuel burning, no emissions at the dock. The same vessel that generates its own power in the middle of the ocean becomes a passive consumer of city electricity the moment it ties up at the quay. Every time you watch a cruise ship leave port, it looks effortless. A structure the size of a city block sliding away from the quay without a single rope attached, rotating on its own axis and accelerating into open water without any visible effort, but it is not effortless. It is a diesel-electric power plant generating enough electricity to run a small town. Azipods rotating beneath the hull, responding to commands measured in fractions of a degree. A distribution system managing 85% of its output for propulsion, and the remaining 15% for everything thousands of people need to live comfortably at sea. Redundant systems standing by in case anything fails. Fresh water being produced continuously from the ocean itself. To me, that is what makes a cruise ship extraordinary. Not the pools, not the restaurants. The fact that beneath all of it, an entire city is generating and managing its own power every hour of every voyage without the passengers ever noticing.